Welcome to the Sleepy Cosmos Stories channel. I'm very happy you're here. Before we begin, I'm truly curious, where in the world are you watching from tonight? A quiet bedroom, a comfortable armchair, or perhaps lying in bed at the end of a long day, simply wanting to rest? Wherever you are, I hope this is a moment where you feel comfortable, safe, and able to let your thoughts gently drift away. If you enjoy these calming journeys through space and would like to hear more, liking the video and subscribing helps this small channel continue its path. And to those who are already subscribed, I sincerely thank you. Your support means far more than you might think. Now, I'll try not to make tonight's topic so exciting that it keeps you completely awake. But if you do happen to stay awake, at least you'll better understand why some stars shine in the dark, why emptiness is never truly empty, and how even in the quietest corners of the universe, light knows how to whisper. A small price to pay for a sleepless night. Shall we begin? When you think about darkness, what do you see? Most of us imagine darkness as an absence, where there is no light, a moment ruled by nothingness. But in the depths of the universe, in those endless black oceans stretching between the stars, darkness is never truly dark. There are lights there that we cannot see, hidden glimmers, silent stories. Tonight, we will journey together to the darkest corners of the cosmos, to its loneliest places. But there is no need to be afraid, because within the darkness, we will discover unexpected beauty. We will find glowing creatures, shining stars, and places where even atoms seem to dance. You don't need to understand everything. You don't need to memorize every fact. Just breathe. You may close your eyes and let your thoughts soften. Because tonight, we will explore the universe's most mysterious sources of light. Slowly, gently, one story at a time. If you're ready, let's begin. First, let me ask you this. Does light only come from the sun? From stars? From fire? Most of us think so. But in the deepest parts of Earth's oceans, in that endless darkness where sunlight never reaches, there is another kind of light. Living light. We call this bioluminescence, the light produced by living organisms from within their own bodies. It looks like magic, doesn't it? But it isn't magic. It's chemistry. Some creatures use a special enzyme called luciferase, which reacts with luciferin and produces light, a blue-green glow, as if a tiny star were burning inside a fish. Jellyfish living in the deep ocean turn into living lanterns filled with trembling neon lights. Some flash suddenly when threatened, as if an electrical storm has erupted in the dark. Others use their light to lure prey. Think of the anglerfish. It has a small glowing organ dangling from its head, like a lure. It swims through the darkness, swaying its light, and curious little fish draw closer. And then the bait becomes a mouth. But perhaps the most enchanting sight is created by tiny organisms, particles of plankton at the surface of the ocean. When you touch a wave in the dark of night, the water glows, as if stars had fallen into the sea. A green-blue shimmer spreads across the back of your hand. On some beaches, when waves crash onto the shore, the sand lights up with living neon, as if the ocean were breathing, releasing light with every breath. Why do these creatures do this? Some to hunt, some to escape, and some simply to exist. Scientists aren't entirely sure, but one thing is certain: darkness is never truly dark. It is simply waiting for the right eyes to look. And this isn't only true in our oceans. In space, in the universe itself, there are hidden lights within the darkness. We just need to learn how to find them. Now, imagine this. A star is dying, but not an ordinary death. A massive star spends billions of years burning hydrogen in its core, then helium, then carbon, oxygen, until there is nothing left to burn. And when that moment comes, the core collapses, suddenly, violently. A supernova explosion occurs. The star's outer layers are hurled into space like a gigantic cosmic firework. But what remains behind, that is the true miracle. A neutron star.
Neutron stars are among the densest objects in the universe. A teaspoon of neutron star material would weigh more than Mount Everest. Can you imagine that? Billions of tons of matter compressed into a sphere the size of a city. Protons and electrons are squeezed together so tightly that they merge into neutrons, forming a kind of super-dense subatomic soup. And these neutron stars often spin at incredible speeds. Some rotate hundreds of times per second, like the brush of a vacuum cleaner, but on a cosmic scale. But here is the truly fascinating part. Many neutron stars have extremely powerful magnetic fields, and these magnetic fields emit beams of radiation from their poles, just like a lighthouse. As the star spins, the beam sweeps through space in a circle, and if Earth happens to be in the path of that beam, we see it as a pulse, a flicker, a whisper. That's why we call them pulsars, beating stars, the pulse of the universe. Some pulsars are so precise that they can rival atomic clocks. They can rotate 600 times per second and never lose their rhythm. For millions of years, the same beat, the most accurate timekeepers in the universe. And this light finds its way through the darkness at the speed of light, silently. Even after the star's death, that light continues, whispering into the depths of the cosmos. I am here. I am still here. But now, let me tell you something even stranger. This time, it isn't a light you cannot see, it is matter you cannot see. When scientists looked at the universe, they noticed a problem. Galaxies were rotating too fast. Mathematically, the amount of visible matter they contained was not enough to hold them together. Stars, gas, planets, everything was accounted for, and yet galaxies were behaving in ways they should not. The answer? There had to be something else there. Something we could not see, much more of it. We called it dark matter, because it does not emit light, reflect light, or absorb light. We cannot see it with our telescopes. We cannot detect it with radio waves. It leaves no trace in any part of the electromagnetic spectrum, but we know it is there because it has mass, and mass creates gravity. Dark matter surrounds galaxies like a vast halo, far larger than the visible galaxy itself. And right now, as you listen to these words, dark matter particles are passing through your body, trillions of them every second. You don't feel them because they do not interact with you. They pass through like ghosts. Look at the universe. Everything you see, every star, every galaxy, every nebula, makes up only about 5% of the universe. The rest, about 27%, is dark matter, and 68% is dark energy. So in truth, most of what makes up the universe is invisible. It's as if the universe has a hidden skeleton, a vast invisible web, and galaxies hang upon this web. Dark matter holds them in place, yet we can never see it. Some scientists believe dark matter interacts very weakly, extremely rarely. Perhaps one particle in billions collides with an atom, and when it does, maybe it creates a tiny signal in a detector. That's why in deep underground laboratories around the world, scientists are trying to catch dark matter. They wait, they listen, they search for that rare collision. But so far, dark matter keeps its secret, the greatest mystery of the universe. Invisible, untouchable, yet everywhere. And of course, if we are talking about lights within the darkness, we cannot skip black holes, because black holes are places where light goes, but never returns. How does a black hole form? Most are born from the death of massive stars. If a star is too large even to become a neutron star, the collapse does not stop. The core keeps falling inward, and it falls and falls forever until it reaches a point of infinite density. We call this a singularity. Around this singularity, there is an invisible boundary, the event horizon. If you cross this boundary, you cannot return, not even light can, because the escape velocity becomes greater than the speed of light. And according to the rules of the universe, nothing can travel faster than light. So once you go in, you are falling into infinity. But black holes are not completely invisible. Things happen around them. As matter falls into a black hole, it accelerates incredibly. Friction builds, it heats up, it glows. Outside the event horizon, a spinning disk forms, the accretion disk. And this disk emits X-rays and gamma rays, bright, violent light. So the black hole itself is dark, but the matter around it is among the brightest things in the universe. Some black holes launch enormous jets from their poles. Streams of plasma are blasted into space at nearly the speed of light. These jets can stretch for millions of light years. With radio telescopes, we can see them, vast cosmic eruptions. And around black holes, even time changes. Gravity is so strong that it bends spacetime itself. If you approach a black hole, time slows down for you. As you near the event horizon, to an outside observer, you appear frozen in place. But for you, everything feels normal until you reach the singularity. Black holes are among the deepest mysteries of the universe, places where the laws of physics break down, where time stands still, space bends, and nothing can escape. But remember this, they are not only darkness. The light, life, and chaos around them form some of the most violent spectacles in the universe. Now, close your eyes. Imagine this. Somewhere in space, billions of light years away, there is a galaxy, a young galaxy, filled with stars, blue, white, and blazing. That galaxy emits light, and that light begins to spread through space. But before that light reaches us, it sets out on a long journey, a journey lasting billions of years. And during that time, something happens. The universe expands. As the universe expands, space itself stretches, and this stretching pulls on light waves as well. Light shifts to longer wavelengths, from blue to green, from green to yellow, from yellow to red. We call this redshift. The farther away a galaxy is, the more its light is redshifted. Some galaxies are so distant that their light shifts beyond the visible spectrum into infrared, microwave, or even radio waves. We cannot see them with our eyes, only with special telescopes. The James Webb Space Telescope collects infrared light for exactly this reason, because it wants to see the oldest, most distant galaxies, those that formed just a few 100 million years after the Big Bang. Those galaxies are whispers from the universe's childhood. Their light carries a snapshot of that time, and that light, billions of years later, is now reaching our telescopes. Think about it. When you look at a galaxy, you are looking into the past. Light does not travel instantly. It takes time. So, if a galaxy is 10 billion light years away, you're seeing it as it was 10 billion years ago. Perhaps that galaxy no longer exists. Perhaps it collided with another galaxy. Perhaps it collapsed into a black hole. Perhaps it looks completely different now. But that light, that old light, is still on its way, still coming, reaching us like a letter from the past. The universe is an infinite time capsule. Every beam of light carries a story. Every photon is a message from a distant past. So what about the oldest light? What is the oldest thing we can see? The answer, light from the Big Bang, but not directly.
For the first 380,000 years after the Big Bang, the universe was so hot and dense that light could not move freely. The universe was a lightless fog. Photons constantly collided with free electrons, scattering again and again, unable to travel any great distance. Then the universe cooled enough. Electrons combined with protons to form atoms, and suddenly light was set free. It could move. It could spread. At that moment, the universe became transparent, and the light from that moment is still out there, still traveling. But after billions of years of expansion, it has been stretched immensely. That light now arrives as microwave radiation. We call this the cosmic microwave background radiation, and no matter where you look in the sky, it is there. Faint, cold, but universal, the oldest light in the universe. If you have an old television that isn't tuned to any channel, about 1% of the static you see on the screen comes from this cosmic light. Yes, some of the noise on your television is literally the echo of the Big Bang. This light tells us many things: how old the universe is, how it expanded, how the first structures of matter formed. It is like the universe's birth certificate. And this light is always there, quietly, surrounding you, passing through your body, day and night, without stopping. A memory from the universe's childhood, a whisper that never fades, never disappears, echoing forever. Now, take a breath, a deep breath. In the first part of tonight, you explored the lights within the darkness, living creatures glowing in the depths of the ocean, neutron stars, the densest beacons in the universe, dark matter, unseen yet everywhere, black holes that devour light but create chaos around them, red-shifted galaxies from the past, and the oldest light of all from the Big Bang. And from all of this, one lesson emerges: darkness is never truly empty. In every void there is a whisper, in every silence an echo, in every darkness a hidden light. Perhaps this is the universe's most beautiful secret. Nothing is ever truly nothing. Emptiness is filled with potential, silence with waiting melodies, darkness with undiscovered light. And you're floating within this vast, hidden universe. Your atoms came from ancient stars. The oxygen you breathe was once forged in a supernova. The dark matter passing through your body is the same matter that holds galaxies together. You are not separate. You are a part of the universe, and it is a part of you. You may close your eyes. You may relax, because in the next chapter, we will go deeper, to quieter places, to more mysterious corners. But for now, just hold on to this truth. Within the darkness, there are always lights. You simply need to learn how to look.
Now, lie back comfortably. Breathe in and let your thoughts slow down, because I'm going to take you to one of the most powerful, most violent objects in the universe. But don't worry, we'll observe it from a safe distance. Imagine Magnetars. Think of a neutron star, city-sized yet heavier than the sun, spinning hundreds of times per second. Now add one more thing to that: the strongest magnetic field in the universe. Earth's magnetic field is enough to move a compass, gentle, smooth, kind. A Magnetar's magnetic field? Trillions of times stronger. How strong? If a magnetar were as close as the moon, it would instantly wipe the data on the credit cards in your pocket. Strong enough to disrupt the atoms in your body. Strong enough to alter the molecular structure of water. But thankfully, the nearest magnetar is thousands of light years away. Magnetars occasionally produce flares, sudden outbursts of energy. Their surfaces crack and rearrange, releasing enormous amounts of energy. X-ray bursts, gamma rays. In a single second, they can release as much energy as the sun emits over thousands of years. In 2004, a magnetar flare was observed from a distance of 50,000 light-years. It was so powerful that it affected Earth's ionosphere and disrupted satellite communications. It lasted only a few seconds, but its impact was felt. Think about that. From 50,000 light-years away, the scream of a star shook our atmosphere. What would it be like to stand on the surface of a magnetar? Impossible, of course, but let's imagine it. Gravity would be billions of times stronger than Earth's. Your bones would be crushed instantly. The magnetic field would stretch your atoms like spaghetti, and the radiation would destroy every cell in your body in less than a second. But from afar, through telescopes, it is something beautiful, one of the most powerful lights in the universe. Short-lived, but unforgettable, as if the heart of the cosmos beats wildly for a moment, then settles back into calm. Magnetars are young neutron stars. Over time, their magnetic fields weaken. After thousands, tens of thousands of years, they become ordinary pulsars. But during their brief, brilliant phase, they are the most dramatic performers in the universe. Silent, distant, yet unforgettable power. Light and magnetism combined, perhaps the most dangerous lighthouses in the universe. Now, let's go even farther, billions of light-years away, back to the universe's youth. There, we will find the brightest objects of all, quasars. When they were first discovered, scientists couldn't understand what they were. Points in the sky that looked like stars, yet were unimaginably distant. Quasi-stellar objects, quasars. But they were not stars. They were far brighter. A single quasar can outshine an entire galaxy, brighter than trillions of stars. How is that possible? The answer lies in the supermassive black holes at their centers. Imagine a black hole at the center of a galaxy with a mass of millions or even billions of suns. Around this black hole, matter accumulates, gas, dust, stars, all being pulled inward. As this matter falls toward the black hole, it accelerates to incredible speeds. It forms an accretion disk, and this disk becomes so hot that it glows, white, blue, ultraviolet, X-rays, emitting energy across the entire spectrum. And sometimes these black holes launch jets from their poles, streams of plasma moving at nearly the speed of light. These jets can extend for millions of light-years, crossing the intergalactic void, and everywhere they pass, they leave energy behind. They leave light. Quasars are signposts of the young universe. Most were active billions of years ago. Now they are so distant that seeing them is like looking back in time. 10 billion, 12 billion, even 13 billion light-years away. Light that shone when the universe was only a few 100 million years old. Today, most of these quasars have faded. The black holes at their centers consumed the surrounding matter. They now exist as calm, quiet galactic cores, like the one at the center of our Milky Way. But that ancient light is still on its way, still coming, and our telescopes are catching it. Messages from the universe's youth, bright, thrilling memories of an era that no longer exists. Quasars are like photographs of the universe's adolescence, energetic, chaotic, and beautifully unforgettable.
And now, let us come to what may be the most violent event in the universe, an event that in just a few seconds releases more energy than all the stars in the visible universe combined. Gamma-ray bursts. These explosions occur at random places in the sky, at random times, without warning. They last for a few seconds or a few minutes, and then they vanish.
But during that brief moment, they become the brightest thing in the universe. There are two types. Short gamma-ray bursts occur when two neutron stars collide, or when a neutron star merges with a black hole. At the moment of collision, an enormous amount of energy is released. Heavy elements are formed: gold, platinum, uranium, and a massive burst of gamma radiation is launched into space. Long gamma-ray bursts, on the other hand, come from the deaths of extremely massive stars, a hypernova. As the star collapses, it forms a black hole at its center, and as the black hole pulls the rest of the star inward, it fires jets in two opposite directions from its poles. These jets move at nearly the speed of light, and everywhere they go, they emit gamma rays. If a gamma-ray burst were aimed directly at Earth from somewhere within a few thousand light-years, the consequences would be catastrophic. It could damage our atmosphere, destroy the ozone layer, trigger mass extinctions. Fortunately, most gamma-ray bursts occur very far away, billions of light-years distant, and they release their energy in narrow, focused jets. So our luck has to be very bad for one of those jets to be pointed directly at us. Still, some scientists think that certain mass extinctions in Earth's past may have been caused by gamma-ray bursts. Did a jet graze Earth hundreds of millions of years ago? We don't know, but the possibility exists. For now, we observe gamma-ray bursts from a safe distance. Satellite detectors pick up several of them every week from different corners of the universe. Each one is a sign of a star's dramatic death. Each one is a scream of the cosmos. Short, violent, but unforgettable. The most powerful flashes in the universe. But now, let's move to something softer, to a melody, to the music of the universe. Do you remember pulsars? Those rotating neutron stars that emit beams of light? With every rotation, a pulse, a flash. These pulses are so regular that they keep perfect rhythm, once per second or hundreds of times per second, but always the same tempo, never drifting. Scientists began listening to these pulses using radio telescopes, and they noticed that if you convert these signals into sound waves, they resemble music. Tick, 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 tick. Or, for the faster ones, tick, 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 tick. As if the universe itself were a metronome, a rhythm section, a drum that plays continuously, never stopping. Some pulsars lose speed over time, very, very slowly, but measurably. Each year, their rotation rate decreases just a little, as if they are getting tired, losing energy. After thousands or millions of years, they may stop, but for now, they are still playing. And some pulsars experience sudden speed-ups called glitches. Their surfaces abruptly rearrange like a starquake, and their rotation rate suddenly increases before gradually slowing again. That brief jump is detectable. It's as if the star has a sudden palpitation. Its heartbeat quickens for a moment, then returns to normal. Pulsars also teach us about space-time itself. As their light travels through space, it's affected by gravitational fields. Light bends, slows, speeds up, and by measuring these effects, we can understand the structure of the space between pulsars. Some pulsars even exist in binary systems, two neutron stars orbiting each other. As they do, they emit gravitational waves, ripples in the fabric of spacetime. These waves slowly alter their orbits, and by measuring those changes, scientists test Einstein's theory of general relativity. The result? Einstein was right again. Pulsars are the metronomes of the universe, its clocks, and its musicians. Silent, distant, yet always playing. The rhythm of the cosmos is hidden in their pulse.
And now, let us turn to a softer, quieter kind of light, white dwarfs. Stars like our Sun eventually become white dwarfs at the end of their lives. They are not compressed as extremely as neutron stars, but they are still incredibly dense, a sphere the size of Earth with a mass comparable to the Sun. In about 5 billion years, the Sun will exhaust its fuel. It will first become a red giant, casting its outer layers into space. What remains at the center will be a hot, white, glowing core, a white dwarf. But this core is no longer undergoing fusion. It is no longer producing energy. It is simply cooling, slowly. For billions of years, a white dwarf continues to shine. First white, then yellow, then red, then infrared, growing dimmer, growing colder. One day, perhaps after 100 trillion years, it will cool completely. It will no longer emit light. It will become a dark object, a black dwarf. But the universe is not yet that old. No star has cooled that much so far. So every white dwarf is still glowing, a light of memory, the final reminder of something that was once a powerful, brilliant star. Some white dwarfs live in binary systems. They steal matter from a companion star, and this material accumulates on their surface. When enough builds up, it suddenly ignites, a nova explosion, bright and sudden, but not destructive, just a flare. Then calm returns. If enough matter accumulates, the white dwarf can reach a critical limit, the Chandrasekhar limit, about 1.4 times the mass of the Sun. At that point, it can no longer hold itself up. It collapses, and a Type 1a supernova occurs. These supernovae shine with such consistent brightness that astronomers use them as standard candles to measure distances in the universe. Because every Type 1a supernova explodes with nearly the same brightness, we can determine how far away it is by how bright it appears. And thanks to these supernovae, scientists discovered that the universe is not only expanding, it is expanding at an accelerating rate. This discovery won a Nobel Prize and introduced us to dark energy. So, white dwarfs are not merely fading stars, they are also tools that help us understand the expansion of the universe. Quiet, small, but important. The aging lighthouses of the cosmos. And now let us come to a paradox. We talk about light, but sometimes we cannot see it because something blocks its path. Interstellar dust. Between galaxies, between stars, there are vast clouds of dust, extremely thin. A human could pass through them and feel nothing at all, but for light, they are an obstacle. As light passes through these dust clouds, it is scattered, absorbed, and redirected, especially blue light. Because blue light has a shorter wavelength, it scatters more easily. Red light, with its longer wavelength, passes through more readily. That's why stars behind dust clouds appear redder, much like the sun looks redder at sunset when dust in Earth's atmosphere scatters blue light and lets red light through. Sometimes these dust clouds are so dense that no light can pass through at all. These regions appear as dark nebulae, patches in the sky where no stars seem to exist. But in reality, the stars are there, we just can't see them. The famous Horsehead Nebula is one such place. From a distance, it looks like a dark silhouette shaped like a horse's head against the sky. But that darkness is not emptiness, it is dense dust. And here is the interesting part. These dust clouds are where new stars are born. Dust and gas gradually gather together under gravity. They grow denser, and eventually the center becomes so compressed that fusion begins. A new star is born. So the very thing that blocks light is also the source of new light. Darkness hides light, but it also creates it. Where does this dust come from? From dying stars. Red giants shed their outer layers into space, leaving behind dust particles. Supernovae, when they explode, scatter carbon, silicon, and heavy elements into space. And in the cold of space, these elements form tiny grains. So the dust of the universe is made from the ashes of old stars, and these ashes go on to form new stars, new planets, and perhaps new life. Everything is a cycle. Birth, death, rebirth, light, darkness, and light again. Now, take a deep breath. Relax. In this chapter, you witness the brightest and most powerful lights in the universe: magnetars, quasars, gamma-ray bursts. You listen to the rhythm of pulsars. You watched the slow fading of white dwarfs. And you explored the paradox of interstellar dust, something that both hides light and gives birth to it. And what have we learned from all this? The universe is not silent. It is constantly releasing energy, emitting light, making sound, keeping rhythm, sometimes gentle, sometimes violent, but never completely still. And you are a small note in this vast cosmic symphony. The atoms in your body came from supernova explosions. The oxygen you breathe was created in the core of a star. And right now, dark matter is silently passing through you. You are not separate. You are part of it. You may close your eyes. Let your thoughts slow down. Because in the next chapter, we will dive into even deeper mysteries, quieter, more distant corners. But for now, just remember this: the universe is always glowing. Sometimes we can see it, sometimes we cannot, but the light is always there.
Lie back comfortably. Take a breath, because now I'm going to tell you about something invisible, inaudible, yet everywhere: the rippling of space-time itself. Imagine a lake, flat, calm, like a mirror. When you throw a stone into it, waves spread outward, circular ripples expanding toward the shore, visible, measurable, beautiful. Now think about space. Space is not an empty stage. Einstein taught us this. Space and time are like a fabric, a texture. And massive objects bend this fabric. The sun bends space-time. The Earth moves within this curved region. We call this gravity, but in truth, we are simply moving through curved space. So what happens if this fabric is shaken? What if something violently disturbs it? That is exactly what gravitational waves are. As two black holes orbit each other, they make space-time vibrate. They spiral closer in a cosmic dance, with each turn faster, closer. And at the final moment they collide, they merge. At that instant, a tremendous wave of vibration spreads outward through space at the speed of light in every direction across infinite distances. As this wave passes through, it stretches and compresses space itself by unimaginably tiny amounts, smaller than the diameter of a proton, yet still real. In 2015, scientists detected a gravitational wave for the first time using the LIGO detectors. Two black holes had collided 1.3 billion light-years ago, and the ripples from that collision traveled all that distance to reach Earth. The detectors captured that tiny tremor. Space itself stretched by less than 1 part in a trillion, and scientists detected the signal. They didn't just see it, they also heard it, because gravitational waves carry frequency, and that frequency can be converted into sound. What does it sound like? Whoop. A short, rising tone, like a brief whistle, a pitch climbing, then silence. That sound is the final dance of two black holes, their spiral inward, their merger, and then their settling into a single, larger black hole. That sound is the song of space-time. Since then,
dozens more gravitational waves have been detected. Black hole collisions, neutron-star mergers, each with a different tone, a different melody. And these waves have opened a new sense for us. Because light only shows what shines, but gravitational waves reveal black holes, things we cannot see, dark events. The universe is no longer only visible, it is now audible. Gravitational waves are not silent, they are simply very, very gentle. But with sensitive detectors, we can hear them, the heartbeat of the universe, its breathing, its collisions. Spacetime is not a silent fabric, it is vibrating, alive, and musical. And now I'll tell you a paradox, that black holes are not completely dark. For many years, scientists believed black holes emitted nothing, not even light could escape, so they would remain silent and dark forever. But in 1974, a young physicist named Stephen Hawking discovered something else. He applied quantum mechanics to black holes and found this: black holes actually glow. Very, very slowly, very, very faintly, but they do glow. How is that possible? Just outside the event horizon, quantum fluctuations occur. Even in a vacuum, particle-antiparticle pairs briefly appear and then vanish. This is a normal feature of the quantum world. But near a black hole, something different happens. When such a pair forms, one particle falls into the black hole while the other escapes. The escaping particle becomes real, it carries energy, and it spreads into space. But energy must be conserved, so that energy comes from the black hole itself. The black hole loses a tiny bit of mass. This is Hawking radiation. The black hole slowly evaporates, losing mass over billions and trillions of years. For large black holes, this process is so slow it seems almost eternal. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate. The universe is only about 10 to the 10 years old, so this is an unimaginably long time. But small black holes evaporate faster, and as they near the end, they grow hotter and brighter. In their final moments, they may end in a burst. So far, no Hawking radiation has been directly detected because it is so weak that it is lost in background noise. But theoretically, it exists. And this raises a profound question. Do black holes live forever, or do they eventually disappear completely? The answer is yes, they disappear. Very, very slowly, but one day even the last black hole in the universe will evaporate. And what will remain? Only photons. Cold, diffuse, meaningless light. Black holes seem so powerful, so absolute, yet even they are not eternal. They too are subject to the universe's cycle. They are born, they grow, and eventually they die. Very slowly, but inevitably.
Now I will tell you one of the strangest truths of all. The vacuum is not actually empty. When you hear the word emptiness, what do you imagine? A place where nothing exists, empty space, pure nothingness. But according to quantum physics, such a thing does not exist. Even in the emptiest corner of space, where there are no atoms, no photons, nothing at all, something is still happening. Quantum fluctuations. Heisenberg's uncertainty principle tells us that energy and time cannot be known with absolute precision. Because of this, for very brief moments, energy can be borrowed from nothing. And this borrowed energy creates particle pairs, one particle and one antiparticle. They appear, exist for a fleeting instant, and then annihilate each other. They disappear. We call these virtual particles. Are they real? In fact, they are, but they're extremely short-lived. You cannot see them with the human eye, but their effects can be measured. For example, the Casimir effect. If you place two metal plates very close together in a vacuum, they are pulled toward each other. Why? Because between the plates, only certain wavelengths of virtual particles can exist, while outside the plates, all wavelengths are allowed. This creates a higher vacuum pressure on the outside, pushing the plates together.
This experiment has been performed. The result? Exactly as predicted. The vacuum is not truly empty. It vibrates, it seethes, it is full of energy. Every point in the universe floats in this quantum sea, invisible, unheard, yet constantly active, as if space itself is not silent, whispering, humming, oscillating. And some theories suggest that the expansion of the universe may come from this vacuum energy. Perhaps dark energy is actually a consequence of quantum fluctuations. We do not yet know for certain, but one thing is clear: nothingness is never truly nothing. Everything, at every moment, floats in a sea of possibilities, uncertain, vibrating, creative. Now, let us tell you one of the strangest truths of all. The light that travels through space is not always at its speed. When you say the speed of light, what does it mean? Light moves about 300,000 kilometers per second, the speed limit of the universe. Nothing can move faster than light. But here's a secret. Light does not always travel at that speed. In a vacuum, yes, light moves at its maximum speed, but when it passes through matter, it slows down. In water, light is about 25% slower. In glass, even slower. In diamond, nearly half its vacuum speed. Why? Because light interacts with atoms. Photons strike electrons, are absorbed, and then re-emitted. This process creates tiny delays, and the overall speed decreases. But some scientists have done something even more remarkable. They have managed to almost stop light. Using supercooled atoms in special quantum gases, they slowed light down to just a few meters per second. In some experiments, they stopped it completely. The photons were stored in the atoms, then released and allowed to continue. As if light held its breath for a moment, then moved again. This is not just a curious experiment, it matters for quantum computers. Because light carries information, and if you can slow or even stop light, you can store information, process it, create quantum memory. But here's an even more intriguing question. Could light have been slower in the early universe? Some theories suggest that just after the Big Bang, the laws of physics may have been different. Perhaps the speed of light was slower than it is now. Perhaps as the universe expanded, the constants themselves changed. If that were true, it would change everything. Our calculations of the universe's age, distances, all of it. But so far, there is no proof, only an intriguing idea. Still, one thing is clear. The universe's speed limit is not absolute. It's flexible, context-dependent. Light is fast, but not always at the same speed. And now let us come to perhaps the greatest mystery of the universe: dark energy. In the 1990s, astronomers were observing distant supernovae, measuring their distances, and they noticed something strange. Very distant galaxies were farther away than expected. What does that mean? The universe is not only expanding, it's expanding at an accelerating rate. They did not expect this. They expected the opposite. Gravity should have been slowing the expansion. But no, the expansion is speeding up. Something is pushing the universe outward. Something is driving galaxies away from each other, and that something is dark energy. But what is dark energy? No one knows. The simplest explanation is this: space itself has energy, vacuum energy. Every cubic centimeter of space carries a tiny amount of energy, but because the universe is so vast, the total energy is enormous. And this energy creates a repulsive effect, like the opposite of gravity. It pushes everything apart. About 68% of the universe is dark energy. That means most of the universe is a force of expansion. So what happens in the future? If dark energy remains constant, the universe will expand forever. Galaxies will move so far apart that eventually each galaxy will be alone in its own small universe, unable to see any others, because light will never reach them. Space will be expanding too fast. Billions of years from now, the sky will look empty. Only our own galaxy, and eventually even that will slowly fade away. This is called the Big Freeze, the end of the universe, cold, dark, lonely. But perhaps dark energy changes. Perhaps it grows stronger over time. Then the universe will expand even faster, so fast that galaxies are torn apart, stars ripped away from each other, and eventually even atoms are pulled apart. This is called the Big Rip. Or perhaps dark energy weakens. Then gravity will win. The universe will stop expanding, then collapse inward. The Big Crunch. Everything compressed back into a single point, perhaps followed by a new Big Bang. Which will it be? We don't know. But for now, dark energy is winning. The universe is expanding rapidly. Galaxies are drifting away. And we exist for a brief moment on a small planet in this accelerating universe. Now, let me tell you a story. The story of a photon. In the core of a star, hydrogen atoms fuse. Fusion releases energy, and that energy is born as a photon. But this photon cannot escape immediately. The inside of the star is extremely dense, filled with atoms. Every few millimeters, the photon strikes an electron. Its direction changes, it's absorbed, then re-emitted. For a photon, escaping from the core of the star to its surface can take thousands of years, sometimes tens of thousands. A random dance, zigzags in every direction, slowly drifting outward. Eventually, the photon reaches the surface and then it bursts into space. Free, fast. At the speed of light, it travels through space, perhaps toward Earth. 8 minutes later, it enters the atmosphere. It scatters a little, creating the blue sky or the red of a sunset. And then, perhaps, it strikes your eye. A molecule in your retina is excited, a nerve signal travels to your brain, and you see light. That photon was born in the heart of a star. It danced for thousands of years, then it traveled for 8 minutes, and in your eye, it gave meaning to existence. Every light you see comes from a journey like this. Every photon carries a story. From the sun, from stars, from galaxies, even from the Big Bang. And every beam of light brings a piece of the universe to you. The past becomes the present. The distant becomes near. Light is not just a wave or particle. It's also a messenger, a bridge between the universe and you. Take a deep breath. Let your body gently relax. In this chapter, you explored things that are invisible yet real. Gravitational waves, the song of spacetime. Hawking radiation, the slow fading of black holes. Quantum fluctuations, showing that nothingness is never empty. The slowing of light, the flexibility of the speed limit. Dark energy, the force pulling the universe apart. And the story of a single photon. These are not things you see in everyday life, but they are all real, all happening right now, around you. Space-time is vibrating, the vacuum is boiling, dark energy is pushing, photons are traveling. And you are lying quietly, comfortably, in the middle of all of it. You are not separate, you are not just an observer, you're a part of it. The atoms in your body came from stars. The light you see began its journey millions of years ago. And right now, dark energy is gently, gracefully, slowly pulling you and the entire universe farther apart. But there is no hurry.
Lie back comfortably. Take a deep breath. And now, we will travel together into a very distant future. So distant that numbers begin to lose their meaning. But don't worry, this is not a sad story. It is a quiet, peaceful story, and beautiful in its own way. Right now, we live in a universe that is 13.8 billion years old, young, lively, filled with stars. But this will not last forever. 1 trillion years from now, the sky will look very different. The formation of new stars will have almost completely stopped. Hydrogen will be running out. Cold gas clouds within galaxies will be depleted. The raw material needed to make stars will be scarce. There will still be shining stars, but fewer and fewer of them. The massive blue giants will have long since disappeared. They live fast and die fast, lasting only a few million years. Medium-sized stars, like our Sun, will mostly be gone as well. What remains are the small ones, red dwarfs. Red dwarfs are the longest-lived stars in the universe. They burn extremely slowly, efficiently. They can use their fuel for trillions of years, but even they do not last forever. The sky slowly grows darker. Galaxies become dimmer, less bright, less alive, and this is only the beginning. 100 trillion years from now, the last star is running out of fuel, a red dwarf. It burned slowly and quietly for billions upon billions of years, but now its hydrogen is gone. Its light fades, its brightness diminishes, it shifts from red to infrared, and then darkness. It remains as a white dwarf, a hot, dense core, but it no longer produces energy. It simply cools slowly over billions of years. When the final star in the universe goes dark, something changes. There are no longer any new sources of light. Only old light remains, the remnants of ancient stars, white dwarfs, neutron stars, black holes. The sky becomes almost completely dark. Only faint infrared glows remain from cooling white dwarfs, and far away the ghostly traces of other galaxies, but they are so distant that they are barely visible. If there were a planet at that time and someone living on it, what would they see when they looked up at the sky? Darkness, nearly total darkness. A few faint points, perhaps very far away, another galaxy, but mostly emptiness. The stars are gone. Nebulae have dispersed. Galaxies have drifted apart. The universe is sinking into silence. But it is not over yet. Now let us move even farther into the future, to 1 to the 10 to the 14 years from now, 100 trillion years. Galaxies are now very different because two things are happening. First, stars are being ejected from galaxies. How? Close encounters. When two stars pass very near each other, one can be flung away. After enough close encounters, a star gains sufficient speed to escape its galaxy. It is hurled into space, drifting alone through the dark void. Over billions of years, galaxies slowly evaporate. Stars disappear one by one. And second, the supermassive black holes at the centers of galaxies consume stars. Stars spiral inward slowly, and eventually they fall into the black hole. They vanish. In the end, galaxies are nearly empty. A few stellar remnants spread across vast distances, and at the center, a massive black hole. Our Milky Way once held about 200 billion stars, but after 10 to the 14 years, perhaps only a few million stellar remnants remain, scattered across an enormous region, trillions of kilometers apart. And even those have mostly cooled, black dwarfs, completely dark, no energy, no light, just cold, dense spheres of matter.
Galaxies no longer look like galaxies. They are merely sparse clusters of points, and at the center, silent black holes.
And now, even farther, 10 to the power of 40 years into the future. Matter itself begins to decay. Protons appear stable, but some theories suggest they are not eternal. They may have an extremely long half-life, perhaps 10 to the 20 years, perhaps longer, but not forever. If protons decay, atoms decay as well. Planets, stars, everything slowly falls apart. They break down into particles, into radiation. We are not certain. No proton decay has ever been observed, but theory allows for the possibility. And if all protons do decay, what remains? Only black holes. But remember, black holes are not eternal either. Hawking radiation, extremely slow, but they do evaporate. But eventually, they too fade away, slowly emitting photons, shrinking, losing mass, and at the very end, with one final flash, they vanish. That last flash may be one of the last bright moments in the universe, very brief but intense, the final breath of a black hole. The universe is completely dark, completely cold, and completely nothing is happening. Particles still exist, but they are spread so far apart that they never interact, trillions of light years between them. An electron drifts through empty space, alone. The nearest particle is billions upon billions of kilometers away. They will never meet. The temperature is near absolute zero. Energy is at minimum. No work can be done. No processes can occur. Entropy is maximal. Everything is as disordered as possible. And paradoxically, this disorder creates perfect uniformity. Everywhere is the same. No differences, no gradients. And most importantly, time stops. Not literally stops, but it loses its meaning because nothing changes. Past and future become indistinguishable. Every moment is identical to the one before it. To measure time, you need change, an event, a process, but nothing is happening, and so time quietly becomes meaningless. Is this the end of the universe? Maybe, or maybe not. Because remember, quantum fluctuations. Even in a vacuum, particles still appear and disappear, very rarely, but if you wait long enough, anything becomes possible. Some physicists suggest that given enough time, a quantum fluctuation could create a small bubble, a new universe, a new Big Bang. In infinite time, within maximum entropy, extraordinarily rare but possible events can occur. A quantum jump. A particle briefly reaches extremely high energy, and it triggers something. Inflation, expansion, a new space-time, and a new universe is born.
But in infinite time, other strange things can happen as well. A quantum fluctuation might not create an entire universe. Perhaps it creates only a brain. Imagine this. Random particles momentarily come together, and by pure chance, they form the structure of a brain. For that instant, it is conscious, thinking, filled with memories, false memories, but the brain believes they are real. And then, a second later, it falls apart, disappears. This is called a Boltzmann brain. Statistically, given infinite time, such a thing could happen. In fact, the probability of forming a single brain is higher than forming an entire universe because it is less complex. So theoretically, in an infinite heat-dead universe, Boltzmann brains may occasionally appear, conscious for a moment, looking around, wondering, who am I? What am I doing here? And then, gone. Disturbing, isn't it? And yet, also a little poetic. Consciousness emerging from chaos, a search for meaning, existing for just an instant. Perhaps we are Boltzmann brains. Perhaps all our memories are false. Perhaps the universe is not what we think it is. Perhaps we are only a quantum coincidence. But probably not, because mathematically, the probability that we exist in a real universe is higher than the probability that we are Boltzmann brains. Strange, but true. Still, it is an intriguing thought. But there is another scenario for the end of the universe, perhaps the most likely one. What if dark energy grows stronger? Right now, dark energy appears constant, but perhaps over time it increases, becomes more powerful. Then galaxies would not merely drift apart, they would be torn apart. Stars would be pulled away from one another, planets would be flung from their orbits, and eventually even atoms would be ripped apart. This is called the Big Rip. One day, dark energy could become so strong that even atomic nuclei cannot hold together. Protons and neutrons separate, quarks are set free, and then, perhaps, space-time itself tears. The fabric rips apart. Not an ending, but a destruction. When would this happen? We don't know. Perhaps in 22 billion years, perhaps in 100 billion, perhaps never. But if it does happen, it would be sudden. Not a quiet heat death, but a violent end. One moment, everything is normal. The next, everything is coming apart. Galaxies dissolving, stars exploding, atoms breaking down, and then nothing. Perhaps not even nothing, just torn space-time, meaningless chaos. But again, this is only a possibility. Perhaps dark energy never increases. Perhaps it weakens. Perhaps the universe collapses inward, a big crunch, everything coming back together into a single point. Which will it be? Time will tell, but it will take a very long time. Imagine this. Far in the future, trillions of years from now, a planet orbiting the last star, a red dwarf, faintly glowing, but still, there is light. And on that planet, a being, perhaps a machine, perhaps organic, perhaps a mixture of both, but conscious, thinking. That being looks up at the sky and sees almost nothing, only darkness. The other stars are gone. The galaxies have drifted away. That being is alone, the final observer of the universe. What does it think? Perhaps it remembers the past, the ancient ages, skies filled with stars, the dance of galaxies, the diversity of life. Perhaps it feels sadness, or perhaps it feels peace, because it witnessed everything until the very end. It saw the entire story of the universe. And then, the last star goes dark. The final light disappears, and that being remains in the darkness, alone. The final consciousness, the final thought, the final moment of, I am here. And then, only silence. But a beautiful silence, peaceful, complete. Take a deep breath. Relax. In this chapter, you saw the distant future, the fading of stars, the dispersal of galaxies, the evaporation of black holes, heat death, the stopping of time, and perhaps new beginnings. Is it sad? Maybe. But it is also peaceful, because everything has an end, and endings are not bad. They are simply natural. Our lives are short. The lives of stars are long, but all things eventually end, and that is beautiful, because without endings, moments would not be precious. Right now, you are living in a universe that is 13.8 billion years old. The universe is young, alive, filled with light. Trillions of years from now, this moment will be forgotten. But now, it is real, and it matters. At this moment, you are seeing the light of a shining star. You are breathing, you are thinking, you exist. This is the gift the universe has given you. Brief but real, temporary but meaningful. In the next and final chapter, we will complete this journey. I will share my final thoughts with you about the universe, about light, and about you. But for now, simply rest, because no matter how dark the future may seem, the present is still bright, and that is enough.
Lie back comfortably.
Your eyes may grow heavy, may close. Let the space around your body soften, because the journey we took tonight is now coming to an end. But we leave something behind: awe, curiosity, and perhaps a different way of looking at the darkness. Tonight, we searched for hidden lights within the dark. We found living creatures glowing in the depths of the oceans. We explored neutron stars, pulsars, and magnetars. We saw the brilliance of quasars and heard the scream of gamma-ray bursts. We listened to gravitational waves. We tried to understand Hawking radiation, quantum fluctuations, and dark energy. We looked toward the beginning of the universe. We asked about what came before the Big Bang. We imagined inflation and multiverses. We counted the first seconds of time. We wondered about the shape of the universe. And then we traveled far into the future. We watched stars fade. We witnessed galaxies disperse. We saw black holes evaporate, heat death arrive, and time itself lose meaning. From beginning to end, from light to darkness, and within the darkness, light again. Now I want to share a few final thoughts with you about the universe, about light, and about you. Let's begin with a truth, often said but never worn out. You are made of stardust. Every atom in your body was once inside a star. Your carbon was forged in the heart of a red giant. Your calcium was created in a supernova explosion. Your iron came from the collision of neutron stars. Your oxygen was scattered into space billions of years ago in the final breath of a dying star. The atoms in your body traveled trillions of kilometers. They drifted through space, gathered in clouds of gas, took their places during the formation of our solar system, crystallized on Earth, became part of plants, animals, and eventually you. With every breath, you draw in the ashes of ancient stars. With every heartbeat, the products of cosmic fusion circulate within you. You are not separate. You are not outside the universe. You are the universe itself, aware, observing itself. As Carl Sagan said, the universe has found a way to know itself, and that way is you. Throughout this night, we spoke about darkness. But did you notice? Darkness was never portrayed as an enemy. Because darkness is not absence. Darkness is simply light that has not yet been discovered. In the deep ocean, sunlight cannot reach, but bioluminescence shines. Black holes swallow light, yet around them unfold the brightest spectacles in the universe. Dark matter is invisible, but it holds galaxies together. Darkness is the background, the canvas on which light shines. Silence is the space that gives melody meaning. Emptiness is the ground on which existence is recognized. Isn't life like this as well? In your darkest moments, small lights appear brighter. In the quietest nights, the faintest sounds are heard. In the deepest losses, the smallest hopes carry the greatest meaning. Darkness is not the name of nothingness. It is the name of possibility, of waiting, of stillness, and sometimes of surprise. When you look into the dark, you are not seeing emptiness. You are seeing potential. Lights not yet ignited, stars not yet born, stories not yet told. Light is a strange thing, sometimes a wave, sometimes a particle, sometimes both, sometimes neither. But perhaps light is more than that. Light is connection. A star emitted a photon billions of years ago. That photon traveled through space, crossed galaxies, moved through time, and finally reached your eye. In that moment, you connected with that star. The past touched the present. Light is information. Every photon carries a message. Where did it come from? How hot was its source? What elements did it pass through? Scientists read light and learn the stories of the universe. Light is life. Sunlight gives energy to plants. Plants produce oxygen. Animals eat plants. You breathe. Everything begins with light. Life is transformed sunlight. Light is art. Why is a sunset beautiful? Because light dances in the atmosphere. Red, orange, pink. Just physics, but it touches our eyes and our souls. And perhaps most importantly, light is hope. When you are lost in the dark and you see a light, you find your direction. We say there is light at the end of the tunnel because light guides, comforts, reminds you you are not alone. All those lights in the universe are not just photons. They are connections, messages, hopes, things that cosmos whispers to you.
There is something strange in quantum physics. Without an observer, particles remain uncertain. When observed, they become definite, as if the universe does not fully make up its mind until you look. This is not only physics, it is also a metaphor. You are the observer. When you look at the sky, you are not only seeing the stars, you are giving them meaning. You are creating meaning. The universe has existed for 13.8 billion years, but before your eyes opened, as far as you were concerned, it did not exist. Now it does, because you are observing it. Every observation is an act of creation. Every gaze makes the universe a little more real. And it is not only the sky, every moment in your life, looking at a flower, looking into someone's eyes, listening to silence. All of these are acts of observation. All of them bring that moment into being. Perhaps the purpose of the universe is to be observed, to be known, to be felt. And you are fulfilling that purpose with every breath, every thought, every quiet moment of awe. You are not insignificant. You may be small, but you are an observer, the universe made conscious, looking at itself. That is not ordinary. That is a miracle. You know that the universe will not last forever. Stars will fade, galaxies will drift apart, black holes will evaporate, time will lose its meaning. But is that sad? Maybe, or maybe not, because impermanence is part of beauty. Why is a sunset so beautiful? Because it is temporary. It will disappear in minutes. Why is a flower precious? Because it will wither. Why is a moment meaningful? Because it will never come again. If stars shone forever, how special would they be? If time flowed endlessly, what value would a single moment have? Impermanence creates value. Loss deepens meaning. An ending gives the beginning its significance. You too are temporary, a few decades, perhaps a century. On the universe's timeline, a blink, a breath. But that breath is real. That moment is yours, and no one can take it from you. Trillions of years from now, the universe will forget everything. But right now, you remember, you feel, you live. That is enough. That is everything. Now, take a breath, a deep, slow breath. Your eyes may close, your thoughts may slow, your body may feel heavy, as if sinking gently into the bed. Allow it. Tonight, you have taken a long journey from the depths of the oceans to the end of the universe. You saw lights, you explored darkness, you sensed hidden forces. And now the time has come, time to rest. Outside, the stars are still shining. Dark matter is still passing through your body. Gravitational waves are still rippling through space-time. Quantum fluctuations are still bubbling in the vacuum. But you are comfortable. You are safe on this small planet, in this warm bed, in this quiet moment. The universe is vast, but this moment is yours, and that is enough. Let your thoughts drift away. Let your breath find its rhythm.
let your body settle into peace. Remember, there are lights within the darkness, and you are one of those lights. If you are still awake, I want to thank you for taking this journey, for opening your mind, for imagining. If you are already asleep, I hope your dreams are gentle, filled with stars, peaceful. This channel exists for people like you, those who are curious, who feel wonder, who search for light in the dark. And every like, every subscription, every silent listener helps this channel continue. For that, truly, thank you. In the comments, you can share which truth touched you the most tonight, or you can simply write, "I fell asleep." Both are beautiful. But now is not the time to speak. It is time for silence, time for dreams, time for rest. The universe stretches endlessly outside. Hidden lights glow in its dark corners. Black holes spin. Neutron stars pulse. Quasars shine. And you are here, resting comfortably, peacefully, as a single note in that cosmic symphony. Good night. Sweet dreams. And remember, there are always lights within the darkness. You just need to learn how to look. Breathe in, let go, let the eyes close, let the thoughts grow quiet, let the light remain in memory, let the darkness hold you. You are the universe is you. Now just